modern cipher, D is the basic design aspect of D is that is a Feistel. Sorry. So Feistel section is a design aspect for all symmetric cipher. Okay, including AES, DES, Bloodfish, Lucifer cipher. Actually, a very first cipher, modern cipher developed by IBM. So Lucifer cipher. Okay, it was developed in the year 1950s, 60s, and I think so. It's also one of the strong and highly secure cipher, Lucifer cipher, but it is developed by IBM. Okay, so not for commercial use, it is for federal security, I think so. But so many block ciphers, successful block ciphers are built on top of this feature section. Okay, so we started this structure yesterday with the basic requirement of confusion, diffusion, and it's a type of cipher for block cipher, block principle, and product cipher. That is a function F we applied again and again. It's a product cipher. Okay, so just to revise this, the input is a plain text, it's a binary data. That binary bit string to be divided into two equal half, left side and right side. And right side part to be given to the function f with another parameter called subkey. Okay, subkey is another component, another thing which is required for the block cipher. Subkey is not a user given data. Subkey to be generated by the algorithm. Okay, so first is subkey to be given to the function f of round 1, and the result to be XOR with the left side component to get a right side part of second round input, and left side is direct substitution. Actually, this part is based on a permutation method, and this part exploits substitution method. So that substitution permutation is available in each round, so that it provides confusion as well as diffusion. And in order to provide better confusion, we are not using key, we are just converting a key into a stream of keys. Okay, so those keys are unique and those keys are applied to each and every round function separately, so that it exploits confusion property. Okay, confusion is to remove the statistical relationship between the key and cipher. Okay, so key is not at all used directly here. Key to be divided into different subkeys based on, again, that is also based on substitution permutation type organization. Okay, and every round depends on a particular key, K1, K2, and so on. Okay, say for example, the intruder, they hack this piece of section. Whenever hacking appears, it starts from the ciphertext. Okay, it will start from this. Okay, because ciphertext is the only available component. Okay, so the intruder hacker will get LE7 500 RE7. So from that, he may able to tamper only one round. Okay, so subkey, this K16 may be, it may be possible to tamper K16. But just by using K16, it is not possible to backtrack this. Okay, this ripple effect is based on different keys. K15 is required, K14 is required. All those keys to be recovered by the hacker, then only we can able to break this system. So that is the idea behind this Feistel architecture. So we have 16 rounds. 16 is actually a guideline by the Feistel, but in each and every cipher is based on different type of different number of rounds. For example, if you take a DS algorithm, it is based on 16. AES algorithm, it is based on 10 round. 10 round is enough to provide a better security. Okay, so the number of rounds, if you increase number of rounds, the security will get increased. That's it. But it also increases the complexity. So all the symmetry ciphers are time-consuming, based on time-consuming operation. It needs some time. Okay, so to perform encryption or decryption, we have to spend at least a minimum time in terms of milliseconds. So that it is not suitable for data in branch security. It is suitable for data in rest security. Okay, so because encryption decryption process is a lengthy process, time-consuming process. Okay, and this entire cipher can be linearly represented by using this equation. Each round, ith round, left side component is based on the previous round right side component. Okay, and the right side component is based on two basic operations. One is a function, another one is XOR. Okay, so it's based on all three elements, that is right side and left side component of the previous round as well as the present subkey. Okay, Ki, Re minus 1 and NE minus 1 altogether. This based on all these things to be used to compute REI. Okay, so this is a general architecture. It's a guideline. So you can define your own function. Okay, you can define your own function. You can apply it here, and you can name it as X cipher. Okay, so but the basic things, basic principles will remain same. Then only we can get the avalanche effect or Shannon component like confusion and diffusion. Okay, so the structure is very simple. So you can define one architecture and you can fit inside this structural model. Okay, so instead of 16 rounds, you can take 10 rounds. Instead of 16-bit data, you can take 32-bit data or 128-bit data. And sub-key formulation is also in your hand. But only one thing is that K1 to K16 should be a unique sub-keys. Each key should be unique. Okay, may not be of same size of K. Okay, K can be a 64-bit key. K1, K2, K3, all these things can be 32-bit key. Okay, so based on this guideline, you can design. But the thing is, most of the cryptography components are based on number theory, okay, and coding techniques. So you can apply a different type of coding technique, hard double transform, convolutional codes, this type of chip sequences. All those things are suitable for using or exploiting in the symmetry set. Okay, so this function you can think in terms of coding technique. Okay, best like pseudo random coding or hard double coding. So those type of coding techniques are suitable for defining the function. Okay, once you define the function, you can apply it and you can design the structure, feature structure like this. And you have to prove that it provides better security in terms of different analysis, linear analysis, and differential group analysis. Okay, so encryption process over. So now we get into the decryption process. For decryption, this will be the input. Okay, LE70, RE70 will be the input. We have to recover LE1, LE0, RE0. So decryption is a reverse process. Okay, so let's this I'm going to use the same page here because I need this diagram also. Okay, let me move this. The input will be the final outcome. Okay, what is the final outcome? This LE70, RE70. This will be the input. Okay, and one more thing is that the key, sub key to be used in the reverse order. Okay, here round 1 key is K1, round 1 key, sub key is K1. For decryption, round 1 key to be K16, the key to be used in the reverse order. Okay, these are the two major changes in the decryption process. Okay, so let's start with LE70 with RE70, the decryption process. Okay. So Feistel decryption process. So the input will be a ciphertext. Okay, ciphertext is actually a binary bit stream, initially represented as LE17 added with RE17. This is actually input. Okay. Now this input to be given to the decryption function. Okay, the input, the first input is C. Now here I'm going to use a different naming convention. This part, the left side part, let it be LD0. Okay, LD, left side decryption of 0. And this part, I'm going to name it as RD0. But both are same. Actually, LD0 is equal to RE70. I'll write it out here. LD0 LD0 is nothing but LE70 and RD0 is nothing but RD0. Okay, so this remains same, but a different naming. And one more thing is symmetric cryptography, encryption, decryption by the same hardware. Okay, the hardware remains same. Okay, so the only one thing is this subkey to be applied the different manner. If you give plain text as input, it produces ciphertext as output. If you give ciphertext as input, it will produce a plain text as output. No separate hardware for encryption and decryption. Same thing, same function to be used for encryption as well as decryption. So here, so that the first round should not be a swapping round. Okay, so encryption process, the first round we did swapping. You see the encryption, we did swapping only at the end. Okay, only at the end. Decryption should also follow the same rule. Okay, so you should not try to reverse back this. Okay, you should not try to recover back this. This one should happen only at the end. Okay, so the first round is like this. Okay, it should be exactly like this because encryption and decryption both are based on the same hardware. So let's get into this. The right side component, the right side is given to the same function. Function also remains same. Okay? A function f, and it takes another input k16, that is last one key, and the result to be XOR. Okay, with this LD0. Okay, and then finally it produces the output. The output will be this is actually a round one of the equation. So the output is LD1 added with RD1. Okay. So this is a first round of decryption process. Let's get into the linear equation for this. The linear equation, I can write like this. LD1 is equal to RD0. Okay. And RD1 is equal to LD0 XOR function of RD0 comma KXT. Okay, so this is for the linear equation for this. Okay. So I'll get into one more round. Then we need to prove that each round undo the effect of each round of encryption process. Okay, let's get into one more round further. So output of this will be output of this RD1. This is actually round one. Round two. This will be LD2 added with RD2, and this input is given to the functional, and another component is K50, and the result will be XORed with LD1. Finally, is pasted down. Now this one is same thing. So let's make a general equation for this. LDI is equal to okay. So LDI is equal to the previous round RDI minus 1. RDI is equal to LDI minus 1 XOR okay, LDI minus 1 XOR function of RDI minus 1 comma A16. Okay, so I can write like this A 16, but I need here I need K15. So K16 minus I plus 1. Okay, let's try this. LD1 is equal to RD0, and RD1 is equal to LD0 XOR with F of RDI minus 1. So RD0 comma K16 minus what is I here? It's a round number. Okay, round is 1. 1 plus 1. Okay, so this will be 16 minus 150. Okay, and I'll only change only one change here. 16 minus I plus 1. Okay, let me take the thing like this. Now let me just try this. 16 minus I. So okay, so 16 minus I plus 1. So this is 1. Round number is 1. 1 plus 1. 16 minus otherwise 16 minus I. So 16 minus I'm sorry, this is not for round one. Round one I have already returned. Okay, so I'm trying to recover. I try to represent this, but I try to get this answer. Okay, sorry. Let's get into this. First, I'll write down the actual equation, actual value, then we'll substitute it. LD2, what is the answer? RD2. LD2 is equal to RD1. RD2 is equal to LD1 XOR with F4 for RD1, comma K15. K15. Now let's apply this equation. LD2 is equal to LDI is equal to RDI minus 1. So RDI minus 1 is 2 minus 1 RD1. And LDI is equal to RD2 LDI minus 1. So LD1 XOR with RDI minus 1. So I minus 1, that is 2 minus 1, so 1. K16 minus I plus 1. Okay, so 16, this is actually a second round. Okay, so 2 plus 1, so 16 minus 2 plus 1. Okay, it's actually 16 minus 16. The round is not first round, this is second round. Okay, so I is 2 here. So minus 2 plus 1. So minus 2 plus 1. So this will be 14 plus 1, 15. Sorry. So no parenthesis here. 16 minus sign plus 1. So don't forget this plus 1 and it will be confusing. So this round is based on K15. So we have to recover K based on this equation. 16. What is the sign? I is a round. Okay. So here it deals with the second round. Okay. Second round. So minus 2 plus 1. So based on this equation, you have to add plus 1. So 16 minus 2 plus 1. Okay. Am I correct? Or still am I confusing? Clear? 16 minus 2, 14. 14 plus 1, 15. K15. They are getting K15. Can you understand this? Or am I confusing you? Getting it clearly? Students, say on to
Yes,
me.
ma'am.
So don't put parentheses because the confusion is because of the book alone. In the book, you can find the 16 minus I plus 1 inside the parenthesis. Every time we recover something, so 16 minus I plus 1. This is the equation. 16 minus I plus 1. Where I is a round number. Number of keys, n is actually 16 here is constant, but in general, 16 is a different number of rounds. Number of rounds minus I plus 1. In general, it will be n minus I plus 1, where n is the total number of rounds. If it is a 10 round and function, 10 minus I plus 1. Okay, number of rounds minus I plus 1. So 16 stands for total number of rounds. Okay, so this is actually a general equation. Okay, so this process will continue. Okay, only at the end we have to do the starting. So before getting into that, you need to prove one important thing because in this the design aspect is we have 16 rounds. Okay, in the recovery process, the decryption process, every round is to undo the effect of one single round of encryption. That means if you have 16 rounds, for example, if you have 16 rounds of encryption, the first round decryption is to undo the effect of 16th round. Okay. Second round decryption will undo the effect of 15th round. Third round decryption will undo the effect of 14th round and so on. So finally, the last round, 16th round of decryption will undo the effect of the first round of encryption. Then what will be the result? The result is a plain text. Okay, so every time you should not try to recover the original data. Every time you have to undo the effect of one single round. Okay, so we need to prove that in pieces section, we need to prove that whether that effect is implemented or not. Okay, so my requirement here is, so in this case, the output is LE70, RE70. Okay, so first we have to undo the effect of this round alone, K16 alone. Okay, so what we are expected here is, okay, in the decryption first round, decryption round 1 is to undo the effect of 16th round. Okay, so if the input is LE17 added with RE17, So what we are expected is, we are expecting this. Okay, so LE16 padded with RE16. This is what we are expecting. Okay, but keep one thing in your mind. Instead of to avoid a side channel attack, we have just introduced a swapping at the end. Okay, so if you undo the effect, you can concentrate only on this. If you undo the effect, you can concentrate only on this, because finally, in the decryption round, final operation is also swapping. Okay, in the decryption, final operation is also swapping. Okay, so what we are expecting here is, if the input is LE17, RE17, we are expecting the swapped output. Okay, RE15 padded with LE15. Can you understand this point clearly? Because swapping is not a first operation, swapping is a final operation. Finally, you have to swap it. Okay, so every time you have to undo the effect of one single round by keeping one thing in your mind. It is a swapped output, not a swap final initially. Okay, the swapping should happen at the final stage. So if the input is LE16 RE16, no problem. You are expecting LE15 RE15. Okay, but input is not LE16 RE16 for final round. The input is LE17 RE17. Then what we expected here, the input to the last round, LE15 padded with RE15, but not like this. We're expecting RE15 padded with LE15 because of this side channel attack restriction. Okay, because finally at the decryption process, we'll do the swapping. Okay, can you understand this point alone? Every round should undo the effect of one single round. So first round of decryption should undo the effect of 16th round. Second round of decryption should undo the effect of 15th round, and so on. Okay, finally you have to do the swapping to recover back the flight text. Okay, so let's check it out, because whatever we are doing in substitution permutation structure, that should be verified by using linear equation. Okay, so to verify this, two equations are mandatory. You also take it out, these two equations. So this one, LE15, sorry, LDI is equal to RDI minus 1. RDI is equal to LDI minus 1 XOR the depth of RDI minus 1, K61 minus I plus 1. This is one linear equation required to prove this. And another linear equation, LEI is equal to REI minus 1. REI is equal to LEI minus 1 XOR the depth of REI minus 1, K. Please keep these two equations in your mind. Okay. So now let's go for a proof for this. The input is LE17 RE17. We have directly substituted LE17 to LD0. Okay. Now, what is actually LD0? LD0. Let's go for the proof here. LD0. What is actually LD0? LD0 is RE17. Okay. So just to substitute it, LE17. Can you understand this? LD0 is simply LE17. Okay. So LE17 is nothing but LD0. Still go for one more substitution. I'll come to this. Okay. Now what is LE17? LE17 is from this RE16. Okay. So LE17 is nothing but RE16. Direct substitution of RE16. Okay. So instead of LE17, I can just change it as make it as RE16. Okay. So just substitute it RE16. Okay, so this is nothing but LD0 is nothing but LE17. This is equal to RE16. This is the first equation we got. Okay. Second thing, RD0. What is it? RD0. RD0. Just substitute it. RD0 is nothing but a direct fraction component. Okay, so this is RE17. Okay, so but what is actually RE17? Let's go here. RE17 is LE60. RE17 is nothing but LE60. Okay, because directly it is swapped LE60. But LE16 is a direct output of RE15. Okay, so I can write it as RE17 is LE16 is equal to, because it is equal to, see. So this is actually direct substitution of RE15. Okay, so LE16, RE15. So substitute it. Okay. So what is this? This is LE16. This is directly is equal to RE15. Okay. So now we got two values here. LD0 and RD0. Okay. So LD0, RD0. LD0 is nothing but RE16. Okay. So LD0 is RE16 finally, and RD0 is LE50. Okay. Can you understand this? Can you understand this?
Yes, ma'am.
Okay.
Yes, ma'am.
Let's try to go further because we derive only input alone. Okay, but what we are expecting, what we need to prove here, this round will undo the effect, not the single substitution. This round, entire round will undo the effect. That means if you perform, if you apply the round one, you will get this output. What is this? LD1 added with RD1. This is a first round output. Okay, this first round output should undo the effect of a final round encryption. Okay, so what is a final round encryption? Final round encryption. This is a final round encryption. You are undoing the effect. That means you are expecting LE50, RE50 at the end of the first round. Okay, LE50, RE50 at the end of the first round. LE50, RE50. LE50, RE15. LE15 added with RE15. You just understand, just a proof here. This round is to undo the effect of 16th round of decryption. 16th round of decryption, the input is LD0, RD0, we derive differently. The expected output is LD1, RD1, that should be equal to LE15, RE15. Okay, but it's not actually LE15, RE15 because finally one swap is missing. Okay, we have not started with swapping. Okay, so finally we have to do the swapping. So this is not expected. The expected thing is RE15 added with LE15. Okay, so this is expected because finally we do swap. Okay, so this round output LD1 added with RD1, this one should be equal to the 16th round input, 16th round encryption input, but in the swap command. Okay, so RE15 added with LE15. This is what an important proof for the Feistel structure. Okay, so if you prove this, then definitely you can defend that this will work perfectly for 7 to 7. Okay, so can you understand the reason for this proof? First decryption round should undo the effect of last encryption round. Okay, so this is an input of the last encryption round 16. Okay, so this is the output of decryption round 1. Okay, but here we have swap because finally we are going to do swapping. Swapping is not a final initial operation, so then we have taken the swap input. Okay, so you need to prove that LD1 is equal to RE15. Yeah, RD1 is equal to LE15. This proof is mandated. Okay, so LD1 added with RD1, it should be equal to RE15 added with LE15. Clear? Clear? Is it clear? Okay, so let's go with this equation. We already derived LD0, RD0. Okay, so we know LD1, RD. LD1 is RD0, RD1 is LD0 XOR F of RD0, K16. Okay, so now proceed this K16. Now we are going to use this one and this one to get into the proof of this. Okay, so LD1 is equal to RD0. Okay, so just proceed further. What is RD0? RD0, we already taken the proof. RD0 is nothing but RE15. Okay, based on this equation too. So RE15. Now LD1 is equal to RE15. That is actually proved here. LD1 is equal to RE15. The first part proved. Okay. Okay. So second, we have to prove that RD1 is equal to LE15. LE15. Okay. So RD1 is equal to LD0 XOR of F of RD0 comma say K16. Now we have to substitute it. Now take it out this equation. LD0. What is LD0? That is RE16. Okay. I'll write it out here. RE16 added with, this is F of RD0. What is RD0? RD0 is RE15. Okay. RE15, RE15, come on. This is actually K16. Okay. So further, just proceed further. Okay. So this is equal to, what is the equation for RE15? Linear equation of RE15. Just apply this equation. Apply this equation. Encryption linear equation REI is equal to LEI minus 1 XOR F of REI minus 1 comma K. Okay, just use this equation. Just substitute this values. What will I say here? What is RE16? Any one of you please tell me. What is RE15? RE16? By applying encryption equation. Can you understand? Can you able to follow me? RE16. Just apply linear equation of encryption process. What is this? REI is equal. Good. And also show you the equation again for your remembrance. This equation will be used. This equation REI is equal to LEI minus 1 XOR F of REI minus 1 comma K. Okay, remember this equation. Okay, just apply this. REI. Now tell me, what is this? REI is equal to
LE16.
LEI minus 1. Yeah.
LE15.
LE15.
XOR
of
F of
oh.
RE15 comma K16.
Good, very good. So this is actually for RE16. RE16 to be substituted based on the linear equation of encryption process. Okay. Now take it out this. Okay. XOR of. Okay. Go further. Let's take it out this. XOR of F of RE15 comma K16. Okay. But irrespective of this function. Okay. Now whatever it may be the function. Whatever may be the complex function, the parameter remains same. RE15, then also RE15. So this is K16 and K16. Okay. So this is one input to this XOR. Now take it out this XOR operation alone. This is one input to the XOR operation. This is one input to the XOR operation. So both the inputs are same because the function remains same. Okay, I said already. Encryption, decryption function remains same. It's a symmetry function, same function to be repeated again and again for every round also. So both the functions are same, both the parameters are same, so you will get same output. Okay, f of x, f of RE15, comma K16 dx, f of RE15, comma K16 dx, x XOR f, x XOR f, sorry, x XOR x, x XOR x.
0, ma'am.
0. So this entire component will be null. So this is equal to RE15. Sorry, LE15. This entire component will be null. So this is equal to LE15. What is this? This is nothing but RD1. RD1 is equal to LE15. Now just come to our proof here. What we are expecting here is LD1, it should be equal to RE15. Yes, we proved that. LD1 is equal to RE15. Next, we try to prove that RD1 is equal to LE15. So that is what we received here. RD1 is equal to LE15. So perfectly it is proved. So every time, every round is used to undo the effect of the previous one. So further you can proceed further. RD1 is a LD2 padded with RD2. Okay, if you take LD2, just go for this is for homework, try it out. LD2 padded with RD2, it should be equal to LD2 padded with RD2. Second round of decryption should undo the effect of 15th round. Okay, what is the 15th round input? LE14 padded with RE14, but we are getting swapped the input. Okay, So LD2 padded with RD2, it should be equal to LD14 padded with RE14. Okay, so just try to prove it. Clear? Is it clear? Because structure not at all a matter. Symmetric cryptography, the structure not at all a matter. Whatever can be whatever the thing that can be picked up to the structure. In cryptography, understanding the algorithm is important. In similar manner, understanding the proof or verification process is something important. For example, you are applying RSA algorithm. Okay, you are encrypting the data, you are decrypting the data. When you decrypt the data, it should recover the original plain text. That proof is not simple. That proof is based on Euler's theorem, Fermat's theorem, Gaussian function, and all those things. Okay, so all the symmetric algorithms are proved mathematically. Okay, by applying some mathematical principle, Euler's theorem or the Gaussian function. But symmetric cryptography is not based on any maths, not even addition. All these are simple XOR operations, substitution, permutation. Binary XOR is matter here. Okay, so symmetric algorithm cannot be proved by using mathematical equations. Okay, linear equation, discrete logarithm problem or Euler's number theory, all those things are not required. So these symmetric cryptography to be proved only by using appropriate substitutions. Okay, clear? Okay, so let's complete this decryption process because we have completed 42 rounds here. It will go further. So now we have 16 rounds of PC structure. So it will proceed further. So final round, 16th round. Okay. Let me take a 16th round, round 15. The input will be RD15. Okay, let me take 16th round. RD15, LD15. LD15, RD15, and this one to be given to the function f, and another input is K1, and this one to be XORed with this. Finally, this XOR operation will be the final output. Okay, that will be RD16. This will be LD16. Okay, but don't forget to do one thing. Final swapping is required. Okay, so otherwise you will get swapped output. Okay, so this is actual final swapping. After final swapping, you will get LD17 padded with RD17. Okay, actually this LD17 padded with RD17 is equal to LE0 padded with RD0. LE RD. LD0 pattern with RD0 is a blood test. Okay. So this is for the piece structure decryption process. Piece structure encryption process and piece structure decryption process. Okay. So D is A is Lucifer cipher. All those ciphers are based on this particular principle. This you have to understand only one equation. This LEI is equal to REI minus 1. REI is equal to LEI minus 1 extra the depth of REI minus 1 from REI. And here LDI is equal to RDI minus 1. RDI is equal to LDI minus 1. XOR of F of RDI minus 1, K16 minus I plus 1. In the examination point of view, normally cryptography is not a theory paper. You get only problems. Okay, in this case, the structure, the possible problem is you will be given with the hexadecimal input. You have to recover back by using these equations. Okay, otherwise you need to prove that the second round under the effect of 14th round also. Okay, you'll get a problem like that. Okay, so with that I'll stop here. This is exploited in DES algorithm. Okay, so DES is purely based on this piece structure. Okay, so DES is purely based on this piece structure. Just I'll start DES today, not an in-depth idea. Okay, how far it is related with the piece structure alone. Okay, so I'll tell you that. Until tomorrow, I will start DES algorithm in the deeper sense. Okay, so the piece structure is exploited in DES. Okay. So DES stands for Data Encryption Standard. Actually, 2001, the first data encryption standard. So DS developed by IBM, okay, but standardized by NIST. But it was developed in the year 1967. In those days, the requirement of modern cryptography was not up to the level. But now modern cryptography is very much important for every transaction in every field. Okay, even cloud storage, we need to secure the storage data in storage. We need to secure the data in transit, and all the computing, cloud computing, public computing, sensor computing, all these things we require security. So the requirement of security is getting high today. But in 1967, this particular algorithm was developed by IBM professional for commercial use. Okay, so one specific vendor in US used this. Okay, but after that it is standardized by NIST based on some regulation and some common modality, and it is being used. But the first attack against CTS was happened in the year 1997. It was developed in the year 1967. The first attack against 1967. The first attack in 1997. So 20 years unbreakable crypto system. Okay. So only in 1997 the first attack against this DS was happened by Shamir. Okay, Shamir is a person involved in the design of RSA algorithm, reversed Shamir and Nadelman. So Shami developed one type of complex, sophisticated cryptanalysis, which is known as differential cryptanalysis. Okay, it's very tough. To break this crypto system, DS crypto system, we need a high-end hardware, high complex hardware. Okay, that's known as DS cracker. The cost of the cracker in terms of $1,000. So that cracker developed by Shami by exploiting differential cryptanalysis. Differential cryptanalysis is a sophisticated cryptanalysis, not a simple attack. Okay, not a ciphertext only attack. This is a chosen plain text attack. Okay, so the cryptanalysis requires a huge amount of data, huge amount of plain text and ciphertext encrypted by using same key. Okay, so the requirement, because all the attacks cannot be launched, it's not possible to launch all type of attacks. Okay, some of the attacks are known as sophisticated attacks. Okay, the sophisticated attack means to launch that attack, we need some extra data. Okay, for example, if you want to launch a DOS attack, a denial of service attack, nothing required. You need a computer with internet connection. Okay, and you need to know the IP address of the server. That's it. Okay, you can keep on sending the sync request to the IP server. That is not a sophisticated attack. Any non-computer person can do it. But some attacks are the sophisticated attacks. Okay, so to launch that attack, you need some extra pre-requesting. Okay, here the pre-requesting is very, very high. That means 2 power 47 paths of plain text and ciphertext encrypted by using same key that is required. Okay, that component is required. Then only we can launch this attack. Okay, acquiring 2 power 47 plain text ciphertext combination with the same key is completely impossible. Okay, so that even though the attack is available, differential cryptanalysis attack or linear cryptanalysis attack is available, still it is in use. Data encryption standard is still in use. One reason is that this attack is a sophisticated attack. We need a powerful hardware as well as input requirement for this is something high. And another reason, in this period of 20 years, 67 to 97, 90s internet era. Okay, so most of the protocols are built on top of internet. Okay, so most of the security protocols are built on top of DS. Okay, so 1990s, the dominating modern cryptography is DS. Okay, so 20 years already in use. Okay, so I already said designing the symmetric cryptography is somewhat costly because we have to implement it in hardware. So that still we are using DS, but not in the standard form, in a slightly different version. Okay, slightly modified version. That version is known as TDES. Okay, even in HTTPS protocol, SMTP protocol, PGP, you may come across this TDES. Okay, triple data encryption standard, slightly modified version. The same hardware can be used with some add-ons. Okay, with some extra fitting. Okay, so reusability is also playing a role. Still, today's time, just like IPv4 and IPv6, we have IPv4 protocol, IPv6 protocol. IPv6 protocol is a demanding protocol, but all the IPv4 routers are not being replaced by IPv6 because all the routers are already equipped with IPv4 protocol. So replacing a completely existing hardware completely by the new hardware is something impossible. So the DES is still in use even in 2021, but the slightly modified version is TPDS. Okay, triple data encryption stack. Okay, so definitely you have to understand DES because today's trending cryptography, DES and UES. So new hardwares are developed with the implementation of AES. Okay, existing hardwares are refined with the add-ons of DES. Okay, so TDDS is equal to the security level of AES. Okay, advanced encryption stack. Okay, so 2001, the first attack raised against the DES. Sorry, 1997. Actually, for 1997, the first attack by Shamir in 1997. Okay, but the AES is the next modern cryptography developed in the year 2000. The reason is that from 1997 to 2001, the project proposal initiated by NIST, so many researchers submitted a proposal with a 5 years duration. The project duration is 5 years, 1997 to 2001. Okay, at the end, totally 100 proposals shortlisted by NIST. Out of 100, 10, the most common, the highly secured proposals are selected by NIST. Those 10 proposals, those 10 crypto systems are still in use. Okay, so among the 10, the top one is AES. Okay, so AES comes from the high competition. Okay, but DES is based on add-on of the IBM Lucifer. Okay, so AES is a very strong crypto system with the basic mathematics, finite field theory. But DES is not based on any mathematics. But the transition from DS to AES in this period, 1997 to 2001. Okay, so AES, the researcher have taken 5 years of contribution to develop this particular algorithm. Okay, so AES is unbreakable still now, but some of the hardwares are still based on DS, but not directly based on DS. A slightly updated version, which is TDS. Okay, so the parent, the precursor of DS is a Lucifer cipher. Okay, so Lucifer cipher is the first cipher developed by IBM. Okay, so it's also a block cipher, product cipher, and based on the feature structure, substructure permutation architecture, number of rounds are 16 rounds. It works on 64-bit data at a time. Okay, 64-bit. So the most of the design aspects of Lucifer cipher is exploited in DES server. Okay, so with this history, we'll start DES with a detailed description tomorrow. Okay, so data encryption standard. You have to understand data encryption standard, then only you can get into the idea of DES. Okay, so we'll start formally data encryption standard. Any doubt related to the feature section? The feature section, the homework or workout here is you try to recover or try to undo the effect of 15th round decryption, so 15th round encryption in the second round decryption. Just go further for one round. Okay, just by using this type of substitution. Okay, try to undo the effect of 15th round encryption by applying this equation. Okay, just try it out. That's it. I'll stop here. Tomorrow I'll continue with DS. Any doubt?